Hello, everyone. Welcome back. So today we're going to talk about a very beautiful, highly influential perspective paper that's been published in Nature Machine Intelligence by some great scientists that you can see their list here. And if you look at the title of the paper that is called like Secure, Privacy Preserving, and Federated Machine Learning. So you might think this is purely a medical paper, but actually as a cryptographer and a security engineer, we see this as a classic system security problems. And we have a massive optimization goal. Of course, our goal is just to collect as much as data as possible, as much as medical imaging as possible, and train our model and get great accuracy. But I have to repeat myself. This is not just about optimization. This is not just about utility and performance. This is also very much about the privacy and the security of data that you are sending. So let's get on the track and see what's going on. I previously mentioned like if you want to train an AI, like you have a central server. So of course you could have multiple servers that or multiple hospital again. So again, hospital A, hospital B. I'm going to repeat this because some people are probably just watching one of the papers. I so just don't want them to be lost. So we have some hospital that they are sharing with an aggregator here. I draw it like that this time. So they share their data. But of course, we know this time that if they all of them share their data, that's not a safe way. So instead, we got to a different conclusion. We said instead of the model share their data, what if they just share their weights? So this is much better because now the central aggregator model or the server doesn't learn about the patient information. But we are false if we make that assumptions because although the server cannot see the raw data, but there are some techniques actually that makes it possible that the server be able to even figure out what was the raw data that is being used for training the models. So, for example, attackers on the server side can use the neural networks, like, for example, GAN, that is generative adversarial network. If you heard about that. So, generative adversarial network. And they can figure out what was the original the raw images that been used for training in hospital A, hospital B, and hospital C. So naively just trying to scrubbing the header is technically insufficient, and medical data is very of course lucrative. People, attackers, are willing to pay for being able to find out what is the original image because the price of this images on the black market is very high. We're talking about like each image, and if you look at the reports by IBM, like each record can be on the black market $300 $400, which is really significant. So we moved on to federated learning that we talked about it, that the model shared the weights, but now we got to another problem that we just talked about it, that the server can reconstruct the raw data. But for solving this problem, we have layer in defense. So I call this layer in or layer in depth or layer in defenses. In defenses. So we have three layers that I want us to talk about. One of them is differential privacy, or we call it DP. The other one is HE, or homomorphic encryption. Homomorphic encryption. And finally, the last part that we can use is the secure multi-party computations. So this is secure And actually, there is one more even techniques, and that is the hardware security. And I'll talk about that shortly today too. So let's look at each of them a bit in depth and see what's going on. When it comes to the differential privacy, I just type here DP, and I just change the color of my pen here. So it mathematically guarantees that an outside attacker cannot tell whether a specific patient was included in the training or not. And it completely stops the membership inference and reconstruction attack. So again, the way that it works is that we add a little bit of noise to our during the training. And again, we can use a Gaussian distribution for adding some noise. But remember, the noise, or here I call it error, it shouldn't be so big. If your noise is very big, it can also destroy the model and you'll get bad performance on your model. So there's a trade-off. If error or noise is so high, then the model performance will drop. But if error is very low, very, very low, then actually the attacker might be able to reconstruct the raw image. So you have to figure out what is the exact value that might satisfy this trade-off. And the second part of that, as I just explained, is about the homomorphic encryption. Homomorphic encryption is the gold standard because is a specialized scheme where the mathematical structure are completely preserved through encryption. So for example, if I say encryption of A multiplied by encryption of B, it can be actually equivalent to encryption of A multiplied by B. And the same for addition. Encryption of A plus encryption of B is equals to encryption of A plus B. So how is important this one? Now, if A is the weight on model A, and here is the weight on model B, now it can be encryption over weight A plus weight B. So you see the model or the server doesn't learn about A and B, it just see the encryption version of A and B and just try to add them up. That's it. But you might think, wow, this is super good and super cool, which is actually true. But there is one problem, and that problem is that this is very slow. And we discuss about it in some other videos, and we'll discuss it further from now on, that this approach is actually very promising, but actually can slow down your algorithm even sometimes up to 1,000 times. There are ways to make it better, and we'll discuss it further later. And secure multi-party computation is that no individual party holds enough information to see the underlying data, which means that instead of sending data to one server, we split the private data or model weights into randomized and encrypted shares and distribute them across a consortium of semi-trusted entities. So if we have here again hospital A, B, C, so each of them are sharing the weight. So for example, this is WA, and also they share a secret. We call it SA, but they don't share, of course, their secret with the server, but they have a secret that they keep it to themselves. This one has WB and secret B, and this one has WC and secret C. But of course, these one are not shared. So SA and SP and SC are kept with the hospital. And whenever they want to do calculation together, they have to, all of them share the secret, or at least the majority have to share the secrets. So they can be able to do that computation. It might be quite tricky now, but we'll get better in that later. So this was about the secure multi-party computation. And finally, the last part is hardware security. So we have some hardwares that are designed that called trusted execution environment. So which means that if you don't trust the server, you can have a trusted execution environment. So the data goes to that trusted execution environment inside the server. So the server cannot see what is inside that trusted execution environment, but it can do the execution on it and then return back the result. But also you have to trust that environment. Otherwise, what if that environment itself is compromised? Then you are in trouble. So the most important point of this paper is 10 points that are shared for a roadmap. So I call them 10-point technical roadmap. Number one, shift to decentralization. So shift to decentralization. So don't use centralized approach. Instead, use decentralized approach, which means that we have multiple hospitals. Each of them share specific parts, not just one server that gets everything. Develop cryptography primitives. So invest heavily in optimizing encryption and quantized neural networks. Number three is map the trade-offs. So systematically, we have to research the exact boundaries between accuracy, interoperability, and privacy. Number four is to design against malicious actors. So consider privacy techniques and encryption techniques. Design against malicious actors. And five is to monitor statistical drift. So is your model stable? You have to check it constantly. So perfect. Now we've got five of them. Number six is to implement machine unlearning. What if one of your user or one of the patients says, I don't want my data to be there anymore? You have to figure out a way that you force the machine to unlearn that. So implement machine unlearning. Number seven is like lower barrier with open source. Lower barrier with open source. So develop some or provide accessible, community vetted open source extension to deep learning. Because of course, if they are vetted, so you trust them better. And number eight is that build auditable system. So your system should be able to be auditable, so you can check it to see does not rely on blind assumptions. And treat data as a scarce resource. So here we have to move away from data that is oversupplied to models. And finally, we have to educate the stakeholders because we have to cultivate this value aligned cooperation by teaching the physician, researchers, and policymaker about the risks. So educate stakeholders. Yeah, okay, that's almost everything. Just let's look at the paper quickly together before we wrap up today's sessions. So this is the paper that we walked through. There are some attack vectors that they discuss on their paper too. For example, re-identification attacks is that determining an individual identity despite anonymization based on other information. Data set reconstruction is that to derive individual characteristic from the result of computation that perform on the data sets without having access to the data set itself. Tracing attacks is meant that we can determine whether an individual is present in the data set or not. Attacking against the algorithm itself, there are like adversarial attacks, which means that you can manipulate the input to alter it, and most often that makes the manipulation of input impossible to detect. And then model inversion attack, that you try to reconstruct the model by observing the model behavior. And some techniques for privacy and security. We have secure by default implementation, which means that system that have designed from the ground up with privacy in mind, and no specialized data handling is required. Anonymization, which means that we remove the personally identifiable information, or PII. Pseudonymization, which means that replacement of the personally identifiable information with dummy entry. And some techniques for security, like that we discuss for the AI itself, and privacy preserving AI techniques for protecting the input and output, and federated learning that you already know, differential privacy, homomorphic encryption, secure multi-party, and finally, hardware security implementation. And also this figure shows that you can do the homomorphic encryption, of course, for the encryption and confidentiality. Also, you can use privacy by differential privacy, provide privacy by differential privacy, anonymization and pseudonymization, and the techniques that we discuss. And also, we discuss about each techniques here in more depth. I already gave you some clues, but you can read more about it in this paper. What is homomorphic encryption? What is secure multi-party communications? So again, can be extended to multi-parties. Processing is performed on encrypted data shares, split among them in a way that no single party can retrieve the entire data on their own. So the result can be announced without any party ever having seen the data itself, which can be recovered only by consensus. For example, one case here is a ballot where the result needs to be known, but the individual voters does not need to be known. So we know that who is the person that got selected, but we don't know which person voted for whom. Secure hardware or secure enclaves, that I just talked about them. Let's see if anything is missing, and there are some great references that you can review. Yeah, hope you enjoyed that, and please read through this paper if you are interested. So that's actually laid the ground for our further conversation. Now we're going to move on with power towards the homomorphic encryption and see what are the challenges there through papers and how we can implement it finally for securing the data. Thanks so much for watching, and see you next session.